Okay, I have a polynomial test review for those of you that are getting ready for a big test here on polynomials, say like in an Algebra 2 honors class. And this goes out especially to Aiden, who is reviewing for his test for tomorrow. This is from the first sheet as far as some of the vocabulary and such. And what I'm going to do is I'm going to also offer examples, and I'm going to work them out, but I'm going to ask that as we get ready to work out an example that you try it first. So you pause the video, try it first, and then see how it matches up with my answer. The very first type of thing that we have listed here is the difference of squares and how to factor it. A difference of squares, remember, is exactly what it sounds like. Difference means subtract, and you have two perfect squares. And notice how they factor into conjugate binomials. What's being squared here in the first terms, what's being squared here in the last terms, and then different signs. That's what makes them conjugate binomials. So here's an example. I'm going to work it out, but first I'd like for you to try it. So pause the video for an instant and then try to work the problem out. Okay, let's see how you've done. This is a difference of two squares. This is 2x times 2x. This is 5y times 5y. And it's a subtraction sign, so 2x and a 2x, a 5y and a 5y. One's a minus, one's a plus. It doesn't matter which one you put first. And that's how that factors. Now let's look at the next type of factoring, special binomial factoring here. We have binomial a cubed plus b cubed. This is called a sum of cubes. A times a times a, b times b times b, and definitely a plus sign. Now I always remembered it because I knew that the sum of cubes and the difference of cubes factored into a binomial times a trinomial. The binomial has the same sign, so if it's a sum, it's a plus. If it's a difference of cubes, it's a minus. But notice here, whatever's being cubed here, whatever's being cubed here. Then from this, you can follow the same pattern for both of these. You take the first term, you square it, first term and you square it, and then this is a plus, this is a minus. So it's always the opposite sign as the binomial. Notice minus, and this is a plus. Then it's the product of the two terms, the a and the b, all right? Then it's always, always, always a plus sign and the last term squared. Always, always, always a plus sign and the last term squared. So this is the pattern. You're going to have to memorize it. I mean, there's just no getting around it. You got to memorize these things. And this is a sum of cubes. Then I'm going to ask that you factor it. So go ahead and factor it now. Pause me and then go ahead and factor it. All right, let's see how you've done. This is a binomial times a trinomial. This is y times y times y. This is 4 times 4 times 4. This is a plus sign, sum of cubes. So a y here and a 4 here. Same sign, same sign. All right? This is a plus, this is a plus. This is a minus, this is a minus. Now, to get the trinomial, I base it on the binomial. It's the first term squared. Then always the opposite sign. Then the product of the two terms, that'd be 4y. Then always, always, always a plus, and then the last term squared. 4 times 4 is 16. Now I kind of hinted into this one as well. Notice the difference of cubes. It's the same thing as what I just had, but a subtraction sign. And notice the two main changes here. All right? So I want you guys, to try this one now. Factor this one. Go ahead and put it on pause, and then factor it, and then we'll compare. All right, here we go. Binomial on a trinomial. Whatever's being cubed here, whatever's being cubed here, which is 2. 2 times 2 times 2, same sign. All right, now I get the trinomial from the binomial. First term, square it. Opposite sign. Then it's the product, 2w. Then it's always, always, always a plus, and then the last term squared is 4. And that's how those three special cases of factoring, difference of squares, sum of cubes, difference of cubes, that's how that works out. If you didn't get it the first time, keep practicing. There's lots and lots of practice that you can find online. Synthetic division. Synthetic division, I know we've practiced that a fair amount, but synthetic division is just kind of a shortcut for long division as long as your divisor is in the form x minus the number. And in this case, I have x plus 2. I might have to think of this as x minus a negative 2. So notice here, I went ahead and set it up. I haven't done the division. I take the coefficients of the polynomial. Now my coefficients are 1 from the 1x to the third. There is no x squared term. You will have to put a placeholder here of a 0. So it's like plus 0x squared there. Then minus 7x plus 9. All the terms are complete descending order. 1, 0, negative 7, 9. The negative 2 goes in the pocket right there from the x plus 2. Kind of always the opposite of what it looks like. Bring the 2 down, then you multiply, then you add. Then you multiply, then you add. Then you multiply, then you add, and I get 15, and I circle that one. I always circle the last one because that reminds me that this is my remainder. My variable is x. My answer is, this is the constant, the linear, the quadratic. This is 1x squared minus 2x minus 3. Remainder, so plus, because it's positive 15, plus 15 all over my divisor of x plus 2. And that's how the answer to my problem there. Now, I want you to try this one, if you would, and go ahead and push it on pause. All right, here we go. I have a 2, I have a 0 because there's no x cubed. Then I have a negative 3, then I have a 0 because there's no x term. And then I have a 1. In the pocket, positive 1. I know it looks like a negative 1, but it has to be in the form x minus the number. Positive 1. So you bring the 2 down, and then you multiply, and then you add, and then you multiply, and then you add, and then you multiply, and then you add, and then you multiply, and then you add. Look at this. This one divides into it evenly. I know it divides into it evenly because my remainder is 0, which means that this, x minus 1, is a factor of this 2x to the 4th minus 3x to the 2nd plus 1. By the way, if you've forgotten the names, 3 terms, trinomial, degree 4, quartic. This is a quartic trinomial. And my answer, notice 1, 2, 3, 4 terms, constant, x, x squared, x cubed. This is 2x cubed plus 2x squared minus 1x minus 1. And that would be the answer to the division. Hopefully you can see that okay. Now I have a whole lot of key ideas and theorems that I'm going to run through here, and I'm not going to spend a great deal of time on each one because we're going to apply these as we do some more problems. The remainder theorem says that if you have a polynomial f of x and you divide it by x minus c, then the remainder is f of c. Look back here. Remember my remainder here turned out to be 15? That's saying that if I plug, if this is my f of x here, if my f of x is x to the 3rd minus 7x plus 9, and I plug in negative 2, if I find f of negative 2, see the negative 2 right here, and go through the steps, so that's negative 2 times negative 2 times negative 2 is negative 8 plus 14 plus 9. Negative 8 plus 14 is 6 plus 9 is 15. See how I get the remainder for the division. So if I divide by x minus c, the remainder is f of c, which is nice because if you want to see if it's a factor and your remainder is 0, you know it's a factor. Next one, Fundamental Theorem of Algebra. The Fundamental Theorem of Algebra says if f of x is a polynomial of degree n greater than or equal to 1, so it's linear, quadratic, cubic, quartic, quintic, if it's degree 1 or higher, and it has complex coefficients, which you probably haven't seen very much of. You've seen real coefficients, but not typically imaginary coefficients, then f of x has at least one complex 0. Now, what your teacher may have said was the Fundamental Theorem of Algebra is actually a kind of an offshoot of this that says that if you have a polynomial of degree n, then you would have n zeros. Not necessarily all distinct, but you would have n complex zeros. So, you know, the higher the degree, the more possible zeros you have, including the idea of multiplicity. Imaginary and complex root theorem. The complex root theorem, or maybe I should call it the complex zero theorem here. Zero theorem says that if f of x is a polynomial and you have real coefficients, and if a plus bi is a 0, then a minus bi is a 0. It's complex conjugate. It's complex conjugate. So, in fact, I'm going to throw the word conjugate in here as well, so that you don't forget, the complex conjugate theorem. And that's really useful because sometimes they'll give you a polynomial, they'll give you 1 0, and they'll ask for you to find the other zeros. So it's handy if you know the complex conjugate theorem, because if the 0 they give you is, say, 3 minus 2i, then you know 3 plus 2i is a 0, and you can start breaking it down a little bit more quickly. The rational root theorem, I know this one isn't your favorite there, Aiden, but it says if you have a polynomial f of x equal a sub n x to the n plus a sub n minus 1 x to the n minus 1, a long drawn out way to write it all out, if we have integers for the coefficients and the lead coefficient a sub n is not 0, and if p over q in simplest form, lowest terms, is a rational 0. If it turns out that it is a 0 of this function f, then that means that the p has to come from being a factor of a sub 0, and the q has to be a factor from the a sub n. The p is a factor of the constant term, the q is a factor of the lead coefficient there, and that's what this is saying right here. P is a factor of a sub 0, the constant term, q is a factor of a sub n, the lead coefficient. Now that comes in handy when they give you, say, cubic or quartic, and they don't give you any of the zeros, and they want you to find the zeros. At least you can go through the idea of finding all the possible p over q's, which we're going to do an example of, and then see which of those, if any, by using synthetic division, turns out to give you a 0. Now, the other thing that, and I wrote this out for you once before, is on end behavior. End behavior has to do with what, typically when you're doing a graph of a polynomial function. Okay, first off, you have to look at the function, and you have to determine its degree. So if I have a function here, and I just wrote something out like this, not very good, you look at the degree, that's the exponent for the highest, the most factors of the variable x here, the biggest exponent there, that's your degree, and the lead coefficient, of course, is the coefficient of that term. So it's all based on the first term, the highest degree term. Now, if it's not in descending order, put it in descending order, or at least identify the highest degree term. Okay, make sure it doesn't cancel out somehow with like terms. So that's my highest degree. If my degree is even, then it's either going to both go up or they're going to both go down. If it's even, they both go up, two hands go up, it's an even number, they both go down. So if the lead coefficient is positive, they both go up. That means as x goes to negative infinity, y goes to infinity. As x goes to positive infinity, y goes to infinity. They both go up. They both go to infinity. You may have to be able to do this, so you start looking at this. Now, if the lead coefficient is negative, then they both go down. All right, negative down, that kind of makes sense. So in that case, if you were writing it out, your y values are both going to down, negative infinity. So as x goes to negative infinity, your y goes to negative infinity. As x goes to infinity, your y goes to negative infinity. They're either both going up or they're both going down if it's even degree. If it's odd degree, then one of each. One's going to go up, one's going to go down, depending on the coefficient there. So in this case, if n is odd, okay, degree is odd, and your lead coefficient is positive, okay, positive up and to the right. It's going to, okay, kind of, hopefully you're seeing it the way I'm trying to draw it here, up and to the right, down and to the left. One goes up, one goes down. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. For a positive lead coefficient, if it's a negative lead coefficient, if a, the number in front of the x to the n, is negative, it's just the opposite. It's going to kind of do something like this, where as x gets bigger, y goes down. As x gets smaller, y goes up. So as x goes to negative infinity, f of x or y goes to infinity. If x goes to positive infinity, f of x goes to negative infinity. Just kind of the opposite of, the way the x's are, the y's go to the different ones. Here, they're exactly the same. All right, now that's most of the vocabulary. So what we're going to do next is we're going to do some examples of problems that might end up being on your test. So if you want to go ahead and pause it for a second, that'll give me time to go ahead and clean this off, and then I'll have some problems written down. So why don't you go ahead and pause me. And here we are. All right. My first example, in fact my first 4 examples are all operations involving polynomials. I have a subtraction one here. Notice the minus sign does not mean multiplication. Don't try to distribute here. We'll get to one of those soon enough. Here we have to take care of the subtraction. Subtract this one minus this one. So if you haven't already done so, give that one a try. All right, pause me. Give it a try. Okay, here we go. This is 2x squared minus 1. I can drop the first set of parentheses. But I think of this as a negative 1 there that I'm going to distribute by. Maybe I should use a different color pen here. I'm going to distribute by, oh, one more, by a negative 1. That's going to change the signs inside. So I'm going to have minus 3x to the third minus 4x squared plus x minus 5. And now I'm going to go ahead and I'm going to look for like terms. I have some like terms here and here. I have some like terms here and here. I like to write my answers in descending order. This is my highest degree term, so it goes first, negative 3x to the third. I'll cross it out. Then I'll combine like terms here, minus 2x squared. I have a plus x right here. And then a minus 1 and a minus 5 is a minus 6, and there's my answer. Make sure you look to see if it's subtraction or addition. Here there's no sign between, so we know it's multiplication. So go ahead and multiply this one out. Go ahead and pause it, multiply. Alright, here's how it's done. I'm going to distribute twice. First by the term 3x in the binomial, and then by the plus 1 term in the binomial. So 3x times x squared is 3x to the third. 3x times plus 4x is plus 12x squared. 3x times a minus 3 is a minus 9x. Now through by the positive 1, that's nice, so that's going to be plus x squared plus 4x minus 3. Look for your like terms. They're going to want the answers simplified, descending order. So this is my highest degree term, is 3x to the third. It looks like plus 13x squared. A minus 9, a plus 4 is a minus 5x. And a minus 3. And there's my answer to the second one. Alright, now this third one is division. And you really have a choice here. You can do long division, which is fine, or you can do synthetic division here, because in this case the divisor is in the form x minus a number, which allows you the luxury of being able to do synthetic division. Looks like I forgot an exponent, so we'll put that exponent right there. Now, go ahead and I would suggest use synthetic division and divide and write out your answer properly. Okay, pause. Alright, here we go. 1, negative 7, 17, negative 14, and in the pocket, 2. Has to be in the form x minus the number. Okay, so I put my total bar, 1 comes down, that's 2, negative 5, I multiply, that's negative 10, that's 7, I multiply, that's 14, that's nice. My remainder is 0. That means this is a factor of this, because my remainder is 0. My constant term, my linear term, my quadratic term, my constant, my x squared. So it's 1x squared minus 5x plus 7, and that is my answer. I did one like that just a little bit ago. Alright, now, this guy over here, you have no choice to do this division but to use the idea of long division. Now make sure they're in descending order, and both the dividend and the divisor are. Make sure that you're not missing any terms, because you'll need to put placeholders there. I have x to the fourth, x to the third, x to the second, x to the first, constant, good. X to the second, x to the first, constant, good. This one is already set up. Go ahead and do the long division. Be very careful with this one. Alright, pause. Alright, here we go. X squared minus 4x plus 6, dividing into x to the fourth minus 2x to the third plus 2x to the second minus 4x plus 24. So I'm going to go ahead and say what times x squared gives me x to the fourth? That's x squared. And notice how I line up my like terms. X squared times x squared is x to the fourth. X squared times minus 4x is minus 4x to the third. X squared times plus 6 is plus 6x squared. Now here's where I have to subtract, but I think it's subtraction, so what I do is I add the opposite. So I'm going to negative, positive, negative, and add straight down. These will cancel. Negative 2x cubed and a positive 4x cubed is going to give me a positive 2x cubed. A plus 2x squared and a minus 6x, that's going to be a minus 4x squared. And I bring down the next term, start the process all over again. Alright, now what times x squared gives me 2x to the third? Well, it'd be positive 2x. So plus 2x right here, multiply, that's 2x to the third. 2x times minus 4x is minus 8x to the second. 2x times a plus 6 is a plus 12x. And again, this is where I would subtract, but I'm going to change the signs and add straight down. This becomes negative, this one becomes positive, this one becomes negative. Those cancel. Looks like I get a positive 4x squared, a negative 4 and a positive 8, and it looks like minus 16x. All right, bring down the next term. It's a plus 24, and one more time. Here we go. What times x squared gives me 4x squared? Well, in this case, it would be a positive 4. So I put a plus 4 there. There's the quotient. I don't know if I have a remainder yet. So now I multiply 4 through this. That'd be 4x to the second minus 16x plus 24. No, my remainder is going to be 0. Because you can see that when I change the signs and add, everything cancels out and I get a remainder of 0. And this guy right here is my answer. That's my quotient. Now if I did get a remainder, let's say I got a 5 here, or 2x plus 5. I'm going to put that over my divisor as part of my answer. So plus like 2x plus 5 over x squared minus 4x plus 6. All right, now in this next example, I'm asking you to evaluate the polynomial function. So the first thought would be, here's this polynomial, here's x equals negative 3. What if I just plug negative 3 in here, 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 and here, and do the arithmetic? It'll work. All right, it might not work the way you want because it'd be very easy to make a silly mistake with signs with all these negatives and with a negative number you're plugging in. You're better off using synthetic substitution, which is a lot like synthetic division. X to the fourth, x to the third, x to the second, x to the first constant. I'm going to write negative 1, positive 2, negative 5, positive 7, negative 2. And in the pocket, I'm going to plug in that number, negative 3, that they want me to evaluate it at. I'm not dividing by a binomial, but it's kind of the same principle here. So the negative 1 comes down. I multiply, that's a positive 3. I add, that's a positive 5. I multiply, that's a negative 15. I add, that's a negative 20. I multiply, that's 60. I add, that's 67. I multiply, well, I just got this feeling I wrote down something wrong. I didn't expect this number. I multiply, that's going to be negative 201. I add straight down, I get negative 203. That is my answer. F of negative 3 equals negative 203. Now again, you can plug negative 3 in here and do all the arithmetic, but there'd be lots of places to make silly mistake with signs. I keep looking to see if I made a silly mistake with sign, but if I did, I don't see it. I think that's correct. And that's how this problem works. So we're going to do some more examples here. I just got to clear the board. All right, let's get after this. Problem number 7. Determine if n minus 2 is a factor of n to the third minus 7n to the second plus 5n minus 1. Well, this is has 4 terms. I almost said trinomial. This has 4 terms. It's in descending order. There are no like terms. And it doesn't look like it's going to factor by grouping. So for me to try to factor this and see if n minus 2 is one of the factors, I don't think that's the way to go. But if this divides into this, I should get a remainder of 0 if it's a factor. So I'm going to use synthetic division. I'm going to put 1, negative 7, 5, and negative 1, and 2 goes in the pocket. That's a 1, that's a 2, that's a negative 5, that's a negative 10. Did I do that right? Yes. That's a negative 5, that's a negative 10, that's a negative 11, and there's my remainder. My remainder is negative 11. It's not 0, so the answer is no. However, if the remainder was 0, then my answer would be yes, that it's a factor. No, it is not a factor in this case. All right, now, I wrote down some information about n behavior a little bit ago. Let's use that information to answer the following questions. Describe the n behavior of polynomial function. By the way, I forgot to say pause on that one. Hopefully you did and tried it before I worked it out for you. So let's look here. We're going to describe the n behavior. We're going to use the limit notation with the arrows and such. You go ahead and work out both A and B here. I'll pause right now. Here's A. Look at the first term. Not because it's the first term, but because it's the highest degree term. This was in descending order. Notice, odd degree, a 3, and a negative lead coefficient. You don't have to write this down. I'm doing that to kind of emphasize it. All right. So if it's odd degree, remember one goes up, one goes down. And if it's negative, it doesn't go up and to the right. That's when it has a positive lead coefficient. It goes up and to the left, down and to the right. So as x goes to negative infinity, it goes up and to the left. This is to the left, so that means that f of x, or y, goes to positive infinity. And just the opposite here. As x goes to positive infinity, f of x goes to negative infinity. That's how he's going to want it written down. Okay? The next one up, I have first term there, highest degree, x to the fourth. I have even degree, positive lead coefficient. Well, remember, when we have even degree, they either both go up or they both go down. If it's positive, they both go up. The y's are going up, or the g of x's are going up. So it doesn't matter if x goes to negative infinity, g of x is getting bigger. It goes to positive infinity. X goes to positive infinity, g of x is still getting bigger. It's going to positive infinity. And that's how you're going to write out the end behavior. Now, some teachers will let them say up and to the left, up and to the right. I don't think that's what your instructor is looking for. So write it out in this notation. All right, the next guy up. Here's a polynomial, nice, neat descending order. Find all the zeros of this polynomial, and they give you that x plus 3 is a factor. That it's a factor. Now let's think about this. This is a cubic. It has degree 3. Based on the Fundamental Theorem of Algebra, or at least its offshoot of the Fundamental Theorem of Algebra, I can have as many as 3 zeros. Now to get the zeros, you'd set this equal to 0, or set this whole expression equal to 0, and then you would solve. Well, it's not going to factor nicely. This one has 4 terms. At best, you could factor by grouping. It's not going to factor nicely. So you have to use this bit of information to help simplify it down. So let's see if you remember how to do this. Go ahead and try it. Here's how you go about to do it. You use the fact that this is a factor. You do synthetic division, 2, 5, negative 6, negative 9. In the pocket, a negative 3, because it's in the form x minus the number, right? 2, this better give me a 0. Negative 6, that's negative 1, that's positive 3, that's negative 3, that's positive 9, that's 0. All right, that part's good. That means that this guy here factors into x plus 3 times, and here's your depressed polynomial, 2x squared minus x minus 3. Now I'm going to erase this because it's kind of in my way, but I use the synthetic division to get the depressed polynomial, and notice that my depressed polynomial is quadratic. I should be able to factor this. And if it doesn't factor, I use the quadratic formula. But I believe that this one will factor. Now if you use the bottoms up method, be careful with this. I think you need a minus 3 here and a plus 1 here. So I do have 3 zeros. I'm finding all the zeros. You said x plus 3 equal to 0. You said 2x minus 3 equal to 0. You said x plus 1 equal to 0. So I get negative 3. Now here I'd have to add 3 to both sides. I get 2x equals 3, divide by 2. I get x equals 3 halves. And here I would subtract 1 from both sides. And I get x is negative 1. So my zeros are negative 3, 3 halves, negative 1. I usually put them in order from least to greatest. There they are. Degree 3, and I ended up with 3 rational zeros. Pretty cool. Over to here. Now I left all sorts of space here because they didn't give me a 0 or give me a factor of this polynomial. I'm going to have to use the rational root theorem. That's that P over Q thing, to see if I can luck into a factor here. Now it's x to the third plus 5x squared minus 4x minus 20, so I'm all set up for synthetic division, but what do I divide by? Well, you divide by fractions that are in the form P over Q, where P, the numerator, is an integral factor of, in this case, the constant term of negative 20. That means P could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, or plus or minus 20. 2, 4, 6, 8, 10, 12. 12 possibilities just for P. Q, fortunately for us, it has a lead coefficient of 1, so Q could only be plus or minus 1. So P over Q is going to be the same thing as what P is. It's going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 5 over 1, plus or minus 10 over 1, plus or minus 20 over 1. Holy moly. So now I have to use these possible rational zeros. Now they're just candidates. I don't know which ones, if any of them are. So we got to test them. So here's where we can use a little synthetic division. I'm going to need all the board here, so I'm just going to put some over here. I'm going to have 1, 5, negative 4, and negative 20. Let's try 1. I usually just start at the beginning and work my way through. So if I try a 1 here, 1, that's 6, that's 6, that's 2, that's 2, that's negative 18, that's no good. Cross out 1. Let's try negative 1. And believe it or not, this is what you have to do. You just exhaust all the possibilities until hopefully you find one that gives you a remainder of 0. So let's try negative 1. That's 1, that's negative 1, that's 4, that's negative 4, that's negative 8, that's positive 8, that's negative 12, and that's no good. So I get rid of those. So let me try 2 next. 1, 5, negative 4, negative 20. Make sure you write these down right. With all this arithmetic, it's really easy to make a silly mistake. Let's try positive 2. 1, that's a 2, that's a 7, that's a 14, that's a 10, that's a 20. Oh, there we go. Now we're cooking with gas. So I am able to find one of the zeros, it's positive 2, which means, let's go back to here, y equals x to the third plus 5x squared minus 4x minus 20 has now become y equals x minus 2, remainder 0, it's a factor, and then use your depressed polynomial here, constant x squared of x squared plus 7x plus 10. And hopefully you can factor this, and it does. It factors very nicely. This is x plus 2, x plus 5. So if I said each one of these equal to 0, I'm going to get my nope, I said 3 and I wrote it down. I'm going to get my 3 zeros here. I'm going to get x equals add 2, subtract 2, subtract 5. So my zeros are negative 5 and plus or minus 2. And that's how I find those. And notice how we use the rational root theorem or the rational zero theorem to find that first guy. We had a cubic, we're going to have as many as 3. And once I got that first guy, what I was left with was quadratic. And that made it a lot easier because then I could hopefully factor using skills for my factoring. So I'm going to clean the board here. I'm going to work a few more problems here. And so anyway, take a breather, okay? Okay, all right, here we go again. All right, now in the next problem, problem number 10, we're going to use what we know about end behavior, and we're going to determine which graph, which function goes with which graph. So why don't you go ahead and try it, and pause. All right, here we go. This is our lead term here because it has the highest degree. It's x to the fourth, and my coefficient is 1. So this is even degree, positive coefficient. It's got to do this. Even degree, positive lead coefficient. So which of my graphs go like this? C does. So this one matches up with C. This next one, it has degree 3, also a positive coefficient. Now remember, degree 3, one side goes up, the other side goes down. If it's a positive coefficient, the right side goes up, the left side goes down. Which of my graphs looks like this? Well, this one does right here, answer D. That's not tough. Here I have even degree, negative coefficient. And this is quadratic, so you should know that it's a parabola. And because the negative coefficient, it's opening downward, which means, remember, they either both go up or they both go down. Well, because of the negative lead coefficient there, they both go down. Which one of these looks like they both go down? Well, A does. Now, these are not the exact graphs. These are just rough versions of them, and that leaves pretty much, it better be answer B here for K. Let's see, negative lead coefficient, odd degree, remember one side goes up, one side goes down, but if it's a negative lead coefficient, it doesn't go up and to the right, it's reversed. It goes down and to the right, up and to the left. That matches up with B. See how it's going down to the right, up and to the left? So this one matches up with B. All right, next problem. State the degree and list the zeros of f of x equals negative 3x times the quantity x plus 2 times the quantity x minus 2 quantity squared. Notice here, quantity squared. Then it says, find and state the multiplicities of each zero, and you're supposed to sketch this. Well, let's start with the degree. This factor is x to the first, that's degree 1. This factor, degree 1, x plus 2, this is degree 1. This factor is degree 1, but there are two of them. So there's two factors of degree 1 here, one factor of degree 1 here, one factor of degree 1 here. We add them up. So 1 plus 1 plus 1 and 1, so that's going to give me degree 4. Okay? Degree 4, notice a negative lead coefficient. You say, well, it's not multiplied out. How do you know it's negative? Well, these are 1 x's. So if you multiply those together, you're just going to get 1 in front of the x to the second or x to the third, and that's going to be times that negative 3x. That's going to give me a negative. So this thing should be kind of like this graph in a way, in that both ends are going down. Find and state the multiplicity of each zero. Well, this is already factored. This is great. I'm going to set negative 3x equal to 0. I'm going to set x plus 2 equal to 0. I'm going to set x minus 2 equal to 0. Divide by negative 3. Subtract 2. Add 2. I have 3 zeros. Now it's degree 4, but I have 3 distinct zeros. That's because this one is repeated, this factor. So it says state the zeros. So let's do zeros here and multiplicity here. So my zeros are 0, negative 2, and positive 2. There's only one factor of the x that gave me the 0 here, so that's multiplicity 1. Only one factor of x plus 2 that gave me the negative 2 zeros, so multiplicity 1. But two factors here, so 2. And you can see that the multiplicities and all that adds up to 4, which is the degree of your polynomial. Now, you've got to come up with a sketch. Well, to come up with a sketch, I'm going to do a couple things here. The first thing I'm going to do is I'm going to use the fact that I have the zeros. Remember how the zeros of a function corresponds to the x-intercepts. My x-intercepts are, where's my pen at? There it is. My x-intercepts are at 0, 0, negative 2, 0, and positive 2, 0. Remember, these are not ordered pairs. That's just the x values of my x-intercepts right here, not that stuff. But because it's degree 1, I know that on this x-intercept, it's going to cut through. On this x-intercept, it's going to cut through. But on this one, degree 2, any even multiplicity, it's not going to cut through it. It's going to touch it and then turn back around the other way. So now, to get an idea of what it looks like, I am going to take the time here real quick, and I am going to make a t-chart. And I'm going to plug in, let's see, how about negative 3, negative 1, 1, and 3 to get an idea. Now, these could be pretty good sized numbers, so you want your calculator close by. So this, plug negative 3 in here for all three x's, I would get 9 times negative 1 is negative 9 times 25 is negative 225. Now I'm not going to make a graph, even though these are 2's, that's going to go down to negative 225, but that tells me I'm down here, I'm working my way to this point, I'm coming up fast. Practically vertical. And then negative 1, I plug negative 1 in, that'd give me positive 3 times positive 1 times 9. So positive 3 times, what did I say, 9? That would be 27, so that's a little smaller, but it's still way up off my graph. So I've got to come up to here, and then it's going to come on back down to here. That's not very smooth, but that's the idea. Now when I get to 1, that would be negative 3 times 3 is negative 9 times 1 is negative 9. Well, let's see, that's negative 2, negative 4, negative 6, negative 8. I'm down about here. So my graph continues down to here, probably starts to curl back around to come to here. But remember I said that this one had degree 2, so it's not cutting through, it's going to come up to it and then turn back around. Let's plug in 3 just to show you. That would be negative 9 times 5 is negative 45 times 1 is negative 45, so that is way down here. So this thing comes up, make it a curve, not connect the dots with the line segments, and then tails back down like that. And that is a pretty rough sketch of what this polynomial would look like. Alright, now, one more type of an example here that I want to do, and then I'll see if I can find anything else that's worthwhile here that's in my sample. write a polynomial equation that has zeros, 3 and 2i. Now, because it's a polynomial equation, and my polynomial, well, maybe I should write instead of polynomial function, here we'll write it as function, that has zeros at 3 and 2i, I have to remember the complex conjugate theorem. Alright, remember that? We were talking about that on the very first part of the video. If a plus bi is a 0, then a minus bi. 2i is the same as 0 plus 2i, so that means 0 minus 2i. So I've got one more. I've got negative 2i now. I've got those three guys. So go ahead and try it. Here we go. F of x is equal to, I've got three of them. I have 3, I have x minus 3, I have x minus 2i, I have x minus a negative 2i, which is x plus 2i. Now, they will probably want you to multiply it out. My suggestion is if you have the two imaginaries like that, multiply those first, because they're conjugates the way with the single terms. I can kind of do FOIL here, but the O and the I will cancel. I'll get x squared, then I have plus 2xi minus 2xi cancel, and then I have minus 4i squared. And remember, I squared is negative 1, so minus 4i squared is plus 4. Then I multiply that out, that's x, I'm doing FOIL here, x to the third minus 3x squared. I'm not doing a pure FOIL here, I'm trying to get the ones as I wanted to put in descending order. So let's see, that would be plus 4x and minus 12. You can double check my work there. But those are the problems that are very similar to your review sheet, Aiden. So hopefully you followed along with this, and of course you have my phone number, so you can give me a call if you don't understand something. And I'm hoping that this helps out. I'm going to double check real quick to see if there's anything left that'll be of some use to you. If not, if I can't come up with anything else, then this is the end of the video. Oh, aren't you lucky? We got some bonus time for you. For what value of k will 2 be a 0 of this function? Now, I know you didn't have one like this on your review sheet, but it's a good problem because it makes you think a little bit here. For what value of k, this being the k here in my function, will 2 be a 0? Can you figure that one out? Okay, 2 is a 0 if you plug 2 in and you get 0. So let's see what happens here. Let's use synthetic division. 1 negative 6k. I know that looks weird. Put a 2 in here. That's a 1, that's a 2. That's a negative 4, that's a negative 8. That's k minus 8. That's my remainder. I want this to be a 0, so I want the remainder to be 0. That means k minus 8 has to be 0. K is equal to 8. Now, I don't know if you'll have a problem like that on your test, but that's kind of a slick little one to see. That happens a lot in Algebra 2. Now, I have one more graph, and I know that the graphs take the longest, but in this case, it's probably good practice to see at least one more. I'd like for you to try it first and look to see how it factors. Okay, here we go. So what I'm going to do here is I'm going to factor a GCF of x out. That leaves x squared minus 3x minus 4, and then x times x minus 4 times x plus 1. So I have three zeros. I have three x-intercepts. When x is 0, when x minus 4 is 0, or when x plus 1 is 0. So I have 0, I have 4, and I have negative 1. So here's negative 1, here's 0, and 1, 2, 3, 4. There we go. Notice that my y's are set up so that I use a scale of 2 on the y-axis here. So now I want to come up with a sketch. These are all multiplicity 1, so they're all going to cut through. There's no turn points like the other graph, or touch points like the other graph. So now what I'm going to do is maybe pick some values. Also notice, positive lead coefficient, degree 3, right? It's going to go probably something like this. For my graph, it's got to go through those 3 points. So pick a few points, x and y, to get an idea. I'm going to probably use negative 2. I might use negative a half if I have the spirit there. I'll use a 2 somewhere in the middle, and then I'll use 5. If I plug negative 2, probably plug it back into the factored form. You can plug it into here if you want. Negative 2 times negative 6 is 12, times negative 1 is negative 12. 2, 4, 6, 8, 10, up, negative 12 is right down here. I just squeezed her on. All right, so it's coming up through here. If I plug in negative 1/2, ooh, negative 1/2. Okay, let's see, negative 1/2. This would be negative 4.5 or negative 9/2, and that'll be positive 1/2. So negative times negative is positive times positive, looks like 9/8. 9/8. Yikes. Let's see, so what I had, negative 12 here, 9/8 here. So 9/8 is a little bit more than 1, so it'd be about here. Plug 2 in. 2 times negative 2 is negative 4, times 3 is negative 12. Oh, I got that negative 12 again. That's kind of nice. So way down here. And then if I plug 5 in, I get 5 times 1 times 6 is 30. So that's going to be off the top here. So it comes up, goes through here, comes back down, goes through here, and then oops, goes through here, and then goes up pretty steep. And there's the graph, and that is the end of your review. Good luck with your studies, and good luck with your test tomorrow.